All right, so we have a problem here, and it's going to be a sample of water, and we're going to give it a lot of energy. I just gave you the boiling point of nitrogen here. So we imagine we have a bottle of water, and I'm going to say 500 grams. It's about 16 ounces, and in liquid nitrogen, and we take it out. We take it out, and we use a blast array to deliver 1 billion joules of energy to the water. The question is, what's the final temperature of the water? So we got 1 billion joules, that's 10 to the 9th joules. That's 10 to the 6th kilojoules. That's a lot. So since it's a lot, we know right now that it's going to boil the water, first of all, and it's going to turn to steam. Maybe it's even going to destroy the water and turn it to plasma or something. But let's go step by step. The water itself, the water is going to start out at this negative 195.8. That'll be the temperature we use. So we take it out. The ice is going to heat up, but the ice can only heat up until it reaches its melting point. Okay, so we Q absorbed is going to equal MCAT. We've got the mass 500. The specific heat of ice, make sure you're using the different specific heat, a different specific heat than for liquid water. And the temperature change. Final temperature 0, initial temperature is negative 195.8. And we get 206,373 joules. I'm reminding myself that's 3 sigs. So that last the last figure that's significant is the 6. Once this ice is 0 degrees Celsius, then it's going to melt. So we use the heat of fusion of water, which is 6.02 kilojoules per mole. So 500 divided by 18 times 6, we get 167 kilojoules. That's also 3 sig figs. The liquid water, once the ice is melted, now we have liquid water. The liquid water is going to heat up. It can only heat up until 100 degrees because that's when it starts to boil. So Q absorbed is going to equal MCAT. We've got mass, specific heat, this is for liquid water. Final temperature is 100. Initial temperature is 0. And we get 209,200 joules, 3 sigs. Then the water boils. So we're going to use the heat of vaporization of water. I have 40.65 kilojoules per mole. You might have a different constant, whatever your constant is. Sometimes the values are rounded, maybe 40.7. 500 divided by 18.02 times 40, we get 1,128 kilojoules. So if you add all this energy together, that's the energy to take the ice from the negative 195.8 to steam at 100 degrees. So all we know how to do with the information in this chapter is to heat up the steam now. We have a specific heat for steam. So we figure out how much energy is left. We got 1 million kilojoules minus the energy to warm the ice, minus the energy to melt the ice, minus the energy to warm the water, minus the energy to boil the water. I circled the significant figure, the last sig fig for each of these numbers. And we get this, but we need to round it to this place value. So I'd say, okay, 998,290 kilojoules left. I'm going to convert that to joules. 9.9829 times 10 to the 8th joules. MCAT, MC, specific heat of steam is 1.996 joules per gram per degree Celsius. Final temperature minus 100. You do the math, and it's 1 million degrees Celsius.